next couple of lectures, I will be talking about deep learning in 2032, 10 years from now. Since I'm a simple futurist, I would like to share some of my ideas. So one of them is generalization and PAC-Bayesian learning, probably approximately correct. So I have 7 lectures. Today, I only focus on part 1, which is generalization and PAC-Bayesian learning. At the end of this lecture, I will come back to this outline and talk about the title of these parts. So overfitting is like memorization. For example, if your deep learning is learning something, you don't know exactly which part of, for example, if it is learning a face, or if it is learning a wheel of a car, you don't know exactly which part it is learning. And that's why explainable AI techniques are emerging. But that's not the way. I mean, if you talk about techniques for explainable AI, that's not the cause. You should attack the cause of the problem, not the result of, not the consequence of the problem. So that's why generalization is much more important than all of these paradigms. So we have, for example, your accuracy. When you increase the complexity, I mean number of nodes, your accuracy for your training, although your training accuracy is increasing, but your testing accuracy is decreasing. So this is the problem of overfitting. And generalization, you know that we have a hypothesis space. So if you, for a different hypothesis, or let's say predictor function, so this is the hypothesis. So at different hypothesis, you have a different loss for training and test. So this gap is called generalization gap. For example, at a different at this hypothesis, which is we have training loss. So this gap is the generalization gap, and this is an infinite dimensional space. I mean, the space of hypothesis space is an infinite dimensional space, because it is a space of functions, because neural networks are just functions. For example, if you talk about a hierarchy of neural networks, you're talking about a set of function spaces. And for example, deep ensembles, a technique that you use to understand the uncertainty, is just a way. For example, you initialize a neural network several times, and because the neural network has a non-convex cost function, so you have different results. And some people try to see what sort of neural networks are convex, and so they call it convex neural networks. So that your solution set lies in a space of, for example, it's a convex set, but not strongly convex, but it is convex set. So it can have infinite solutions, but it is not strongly convex. So that's the topic of convex neural networks, which is booming nowadays, that we understand that deep learning has some problems and we should understand it. So yes, this is model complexity and sweet spot. I mean, at some point, everything is okay. I mean, training error is decreasing and testing rows is starting to rise. So that's the time to get out, and that's the point to make decision. So PAC is probably approximately correct. And the goal is that with the high probability, probably, the selected hypothesis will have low error within the band of PAC prediction. So it's approximately correct. So the probability of being approximately correct is greater than, for example, 95%. For example, your delta is just 5%. And I have an example here that, for example, a hypothesis label says that all of these points is positive. For example, we have positive and negative label, a binary classification, and you'll see there is a mismatch between these two, and if the mismatch is too big, so it's too bad. Sometimes there are very few intersections, so it's very bad. So we want to reduce it, but we can do it with PAC learning. So PAC, it is not just telling us the bound of, but also it is telling us how to reduce it. And if we know which variables, which functions are responsible for this reduction of generalization bounds, so that we can use those functions, those bounds that we have discovered, and see it as a loss in our machine learning, so that not only we can observe the generalization bound, but also we can actively reduce it. So the hypothesis space, you should think about it as a space of functions. And because space of functions, for example, Wx, and then you act an activator in neural networks. So W, for example, you can sample it from a distribution. So although the function space is infinite dimensional, but if you parameterize that, like W, you can say that you can handle that with some parameter. And this is a naive way of dealing with these infinite dimensional function spaces. But it's very interesting that we have in neural networks, we look at the weights of that, and we put prior and see the posterior, and look how we are correct. And we can see for each neural network the generalization. But here we actively try to reduce this gap. So when I say target conceptual space, it means that the thing that we don't know the distribution of data. In machine learning, if we always say that it is sampled from a distribution in a IID, identically independent, but we cannot do that. So it's just an assumption that in machine learning we make it. Just like assumption that physicists say. For example, when they want to create string theory or something about black holes, dark matter, warping in space, and all of those things is like philosophy. It's based on some assumptions. So it's like a pseudoscience. But here in machine learning, it's less pseudoscience. Our assumption that's saying that we are sampling from a distribution could be correct if we use it properly. So finite or infinite case. So with high probability, with probability greater than 95%, we can say that R out minus R in is less than this. And H is the size or cardinality of hypothesis. space. So finite hypothesis space, consistent learner case, and agnostic. But infinite hypothesis space, VC dimension is very hard to deal with. And it is a loose bound. But PAC bound, it's very tight. But VC bound is loose, it's very hard. Not only it is loose, but also it is hard to estimate. Even if you use structural risk minimization. And so this is the bound. This is the VC dimension, and you have M samples, and everything is like that. So the empirical risk in sample, when you want to do training, so this is for training. And so it depends on your M samples. So everything depends on M samples. Out of sample, we don't know it. It's expectation, but with the assumption that you know the distribution of your data. For example, in ImageNet, you don't know any distribution. Billions of images, for example, you have billions of images. You don't know the distribution. But you want to reduce this out of distribution. So this is for the test case. You want to know out of sample, out of training samples. And you want to reduce this. So how can we reduce this? This is the generalization bound. It's a safety check, because in healthcare, everything is critical. You cannot just say, okay, this is great accuracy and we don't care about testing time. At test time, this is a problem of life or death of a patient, so you should care about it. So if you like humans, if you like to improve healthcare, you should care about generalization bound. So it's a big issue. So R out minus R in is less than epsilon of M and delta. So delta is your confidence, M is number of samples, and our R out is big, because if you the more data you add, the generalization error, the risk increases. But it cannot be increased more than this amount. And if you design this, it's a matter of design. So if you design this, then you can have a better generalization. Then few people die because of your diagnosis in healthcare. So PAC. So with high probability, so 1 minus confidence parameter, which is delta, and delta usually 5%, generalization error of hypothesis is controllable. So the probability that risk is less than in-sample risk plus some variable is greater than 95%. So we are pretty sure that this is correct. That's why we say it is approximately correct. And for finite function class, as I said, we have this bound. And this is the cardinality of your hypothesis space. And confidence level 5% is delta. And what is PAC-Bayesian learning? As I said, we are dealing with hypotheses. But why do we stick with just one hypothesis? We want the best of. We want to put to understand what if we put a prior. We put a distribution on the space of hypothesis. This is the Bayesian approach. And we look after learning. So after training, you get the posterior. You see how if the posterior is too different from prior, You have a bad generalization. But if your posterior is very close to your prior, that means that you're going to have a good generalization. So prior always is P and posterior is Q. So posterior is distribution over hypothesis space after working with training data. But the prior, usually say that prior is a Gaussian centered it's at origin, for example, just because of simplicity. And so prior is distribution over hypothesis space. You know, putting a distribution in a function space is really difficult. But because our distribution is parametric, for example, a Gaussian distribution has parameter mean and variance. So we have parameters, we have parameterized that. That's why we can somehow control this function space. So that's why we can put a distribution over hypothesis space, over, we call it a function space. Hypothesis space, always think about it as a function space. Function space like Sobolev space, like any Hardy space, Hilbert space, any function space. And PAC-Bayesian learning, we are still proud that McAllister theorem is still useful, and we are in 2022 we are still using this. So it's a very powerful theorem. And we have very few theorems like this in machine learning, unfortunately, very few. But they are elegant, they are great, they are beautiful. Because if you know the KL divergence between posterior and your prior, if you reduce that, you have a better generalization. And also, you have sample and the confidence as well. So it's exactly the same thing, but we have a KL divergence. And we can prove this theorem. It's very easy to prove this. So in PAC-Bayesian strategy, you can use it for learning, for machine learning as well. It's not just a bound. It's not just a measure of how good you're doing. You can also actively use that and simultaneously get the generalization gap and a good estimation, a good predictor, a good hypothesis. So error on seen data is less than error on sample plus some complexity term that we want to reduce. So that's why we minimize this R in plus F. And we can solve it by stochastic gradient descent, Markov chain, Monte Carlo, or any variational inference method you like. This is MCMC is my favorite. For example, Hamiltonian MCMC, Langevin MCMC. It is very accurate, but but people argue that with high-dimensional data you cannot do that. Come on, MCMC is old. But I say that MCMC is powerful. It's we should design our problem in such a way that with only small dimensions you can handle this. And that's why people, for example, talk about variational inference. The techniques of variational inference, for example, in latent Dirichlet allocation, they use it, or many algorithms in graphical modeling, in probabilistic graphical models, and in machine learning, variational inference plays an important role. For example, in variational autoencoder, we use variational inference. So this is a very important theorem that for any function, for any phi function, so phi is a function. We can say that this holds. And I want to prove this. So I just used the beautiful slide of Benjamin. He works in India and also in UCL College London, and also somewhere else I forgot. But he's a very